Hi everybody, we are continuing with circuits. This is 4.4, using all three rules together, level 2. If you are in Physics 101, Physics 112, Physics 131, or Engineering 102, please read Coletta, chapters 18-2, all of chapter 19, and all of 20. Okay, if you haven't done that. And we are going to go ahead and begin. So here's a reminder of all the rules. This is in your notes section that you could download. Have these handy as you're going through the puzzles. So Ohm's law is, actually it is I is equal to V over R. That is, one other computation of that is voltage can be computed as I times R, and resistance can be calculated to be V over I. The Kirchhoff's junction rule says this: amount of current flowing into the junction is equal to the amount of current flowing out of a junction. The consequence of that is series. If you have two components that are in series with each other and you know the current on one of those components, then you'll know the current on the other component. We're going to add to that another sub rule to that. If you have two resistors that are in series with each other, you can add up those two resistances, and that they will behave just like one resistor having the sum of those two resistors. And I'll talk about that in a little bit. Kirchhoff's loop rule, number 3 here, is this: the sum of the voltage supplied is equal to the sum of the voltages consumed by a resistor. Basically, all the resistances in a circuit, basically in a loop, you could add up the differences and that should be equal to 0. Basically, the net, the amount of voltage created is the amount of voltage consumed. The consequence of that is if you have two components that are in parallel with each other and you know the voltage on one of those components, that is the voltage on the other one. And what we're going to find out later on is that if you have two resistors that are in parallel with each other, you can merge them together and they will act like one resistor, which is the product of those two resistors divided by the sum of those resistors. Okay? Now, again, when we move on to the puzzles, I want to remind you that you can't get fractions in these puzzles, although in real life you can get fractions. You could have fractional resistances, fractional voltages, fractional currents. But in these puzzles, to help you check yourself, you want to make sure that everything ends up to a whole number. Okay? So let's move on, and we're going to go ahead and talk about how resistances, two resistors in series, will add up to one resistor. All right, here we go. What we'll have is we have a power supply or a battery or a voltage. It's creating an EMF, and we have a resistor R1 that is in series with R2, and this is all on just one loop. So the current leaves the top end of the battery, goes through resistor 1 and resistor 2, and goes back in. So they're both getting the same resistor, and everything is getting they're both getting the same current. And there you go. Well, if you take these two resistors and add the two resistors up, they will behave just like one resistor that is the sum of those two resistances. Okay? And so a trick that I've learned is just work with two resistors at a time. Add two resistors up. If you have another, so add those two resistors up and imagine that is just one resistor. And then if you have a third resistor, add that to the one sum. And then if you have a fourth one, add that to the other sum, and it'll appear like one resistor with the sum of all those resistors. Okay? But it's best done in practice. So let's move on and let's practice this. All right? This is a puzzle, just like the other puzzles. Again, we want to know what the resistance, current, and voltage is across each component. Don't stare at the cute kitty who is obviously staring at you, wondering what is happening. We have a battery right here that has a voltage of 300 volts. We don't know the current being produced. We have a resistor here that is 50 ohms. We don't know the current and voltage, the voltage being consumed by this resistor. We don't know the current going through R2 or the voltage being consumed by R2, but we do know the resistance is 100 ohms. So go ahead and apply the rule that two resistors in series are going to be equal to one resistor that is the sum of those two resistors. Go ahead and apply that now and hit pause and finish this puzzle. Okay, we're back. I'm going to go ahead and do this, and I'm going to use the markup tool in Adobe Reader. So I'm going to go to comments. Can hit the comments. It again, for some reason, pops out this list of comments, and I'm going to push it back in. All right. I have a text box. I have a pencil. I have an eraser, and I have shapes that I could draw vectors. I am going to be using this to draw the current. Okay, so the first thing I'm going to do is I like to trace the current. And I'm going to turn that to red. Okay, so here's my little vector. So I have a current leaving. And again, the current that leaves the battery is the current that goes back into the battery. This is one line. There is no junction, so the current that leaves the battery has to be the same amount of current that flows in. So it's the same amount of current that's flowing back in. And now I'm going to just track this current over every component. You may not have to do this, but I like to do it just to practice. So you have that current, that red current that's going across the top wire. This same current is going to flow down through R1, and R2 is going to get the same amount of current. And then finally, oops, this same current is going to flow across this bottom wire and then go back in. So I've tracked the current, and now I want to start the problem. All right. So let's see if we could start with Ohm's law. Let's go in kind of order of the rules. Rule 1 is Ohm's law. So in order to do Ohm's law, I need two of the variables. I need I, V, or R. I need two of those to calculate the third one. I only know the voltage here. I don't know the voltage or current. I only know the resistance. And here, again, I only have one variable, which is resistance, so I can't apply that. Let's go to Rule 2. Rule 2 is the junction rule. I need to know the current flowing across, and I don't know the current across any of those components, but one of the sub-rules is this. If I have two resistors, okay, that are in series with each other, and I know the resistances of those, well, then I could calculate the overall current. So what this is going to happen is it's going to turn this circuit into one circuit, okay? And I think I could draw that. So I'm going to basically turn this guy into one circuit, okay? And oh, that is supposed to be, I'm trying to draw a battery, and hold on a second, I'm going to hook up my little tablet here. So I'm trying to recreate this exact little guy here, and for some reason I popped out of this. Here we go. And I'm just redrawing this battery right here. This is battery 1. And what I'm going to do with Kirchhoff's junction rule. And the sub rule is this: if I have two resistors, I could put them together as if they were one resistor. Well, this one resistor is the equivalent resistance, and that's equal to R1 plus R2. Okay, which that is then equal to R1 is 50 ohms, and R2 is 100 ohms. So if you have two resistors in series with each other, sum them up, and they will behave just like one resistor that is the equivalent resistance. So this is 150 ohms. Okay? So now that I've put this together, this is 150 ohms, and this battery is producing 300 volts. 300 volts. Well, now this is a pretty easy problem, right? Because if this is producing 300 volts, this is consuming 300 volts, right? And 300 volts, then, now we could apply Ohm's law. We have two of the variables. So we did the third rule, Kirchhoff's loop rule. The total of this loop needs to be 0. So this creates 300 volts. This consumes 300 volts. So that adds up to 0. So this is 300 volts. This is getting 300 volts. It's 150 ohms. Let's apply the first rule, which is Ohm's law. To get the current, voltage divided by resistance is current. So that is going to give us 300 volts divided by 150 ohms is 2 amps. So now we know that this is 2 amps. This is 2 amps. This is 2 amps. Everything is getting 2 amps. So we use that to give us the current across all components. And what that tells us now is that this has got to be 2 amps and this has got to be 2 amps. And that means the battery is producing 2 amps. All right. And once we have that, now we could let those two resistors pop back out, and they'll still be getting the same amount of current of 2 amps. And now we could calculate the voltage that each one of those guys is consuming, because we have the current across everything. Okay. So now the voltage here, so to get voltage, you get resistance times current. So 50 ohms times 2 amps is going to be 100 volts. And the voltage here is 100 ohms times 2 amps, which is 200 volts. And let's check our work. 300 volts, 100 volts is being consumed, 200 volts is being consumed, and that must mean that there are 300 volts is being created. So that's how you do this one. Okay? So whenever you get two resistors that are parallel with each other, add those two resistors up. They behave just like one resistor, and you're going to use that to find the current. Once you get that combined resistance, that sum of that resistance, look for something that is in parallel with it, and hopefully you'll have a voltage associated there, and that means you'll know the voltage on that one resistor, and you could get the current. All right, let's move on to the next part. So what we talked about earlier is that a sub-rule here is Kirchhoff's loop rule, is if you have two resistors together, they behave like the product of those trees. You could reduce those down to one resistor that behaves like the product of those resistors, those two resistors divided by the sum of those two resistors. Okay, so how did we get that? Well, that comes from this. Essentially, if you have, you start out with how to calculate that. How this comes about is it's actually 1 over an equivalent resistance is equal to 1 over one resistor plus 1 over the two resistors. Now what we're going to do is we're going to try to combine those two resistors together. So R2 times R2 divided by R2 divided by multiplied by 1 over R1 plus 1 over R2 times R1 over R1. And now we have a common denominator. R2 divided by R1 plus R2, and R1 divided by R1 plus R2. And now we have this. That's our common denominator. And now when we flip both sides, and here is the final product of that. You can do this all together with multiple resistors. I like to do just 2 at a time, and that way I can just do it in my head. Okay, so if you have 3 resistors that are in parallel, combine 2 resistors, and now that'll be 1 resistor, and then use that combination of resistors now to combine with the other resistor, and just doing this product over sum. Okay, and that's what we have here. Here we have an EMF or a battery or voltage. We have 1 resistor, R1, that is in parallel with R2. So you know the voltage here is equal to the voltage here and the voltage here. Okay, they're the same voltages. I don't know why they subscripted them different, but they're the same voltage as the one supplied here. All right, so you could combine these 2 resistors, R1 and R2, together to 1 resistor, and that is basically this part right here, R1 times R2 over R1 plus R2, and that's what this is. Okay, so let's go ahead and practice this. Again, we're going to be asked to get what the current, the resistance, current, and voltage of each component below. Here we have a battery that is supplying 3 amps. We don't know the voltage. Here we have a resistor, 3 ohms. We don't know the current and voltage. And we have another resistor that is in parallel with that, with R3, that is 6 ohms. We don't know the current and voltage. So go ahead and try this. Combine the 2 resistors together to get 1 resistor by doing product of R2 times R3 over sum of R2 times R3, and then fill out the rest of the problem. Okay? Go ahead and pause the video and try that now. All right, we're back. Let's go ahead and do this. What I'm going to do again is I'm going to go ahead and track the current. So the current that leaves here, I'm doing this again. I like to do this. It helps me think about the entire problem. By tracking the current, I could think about what is in parallel, what is in series, and it helps me identify that stuff. And it's a good habit for me. It may not be a good habit for you. You might be better at this than I am. But we know the current that leaves the battery is going to come back in, okay, because that's the junction rule. And we know that full current that is leaving the battery is coming up to this first junction. And that means it has to leave the junction on the opposite side. Down here. Okay, so we have a current coming into this junction. So here's where things are going to get a little bit strange. Well, not strange, but oops, didn't mean to do that. What I'm going to do is I'm going to draw a voltage leaving across. So you have a red voltage, you have a red current coming in, and you have a green current leaving. That green current is going to be heading down through R2. And it's going to be heading back into the lower junction. Okay. I'm going to draw a different colored current because it is a different current going through R3. Now R3 is getting its own current that is separate from the green current and red current. Green plus, so red current comes in, green leaves, blue leaves. So that means red is equal to blue plus green. And that means when blue comes down to this lower junction, it's going to combine with green to make red again. Okay? All right. All right, so now that I've kind of thought about it, that means that R2 and R3 are in parallel with each other. Parallel means they get their own separate currents from each other. So everything is in parallel with each other. R2, the battery, R2 and R3. That means if we know the voltage across the battery, we know the voltage across R3 and the voltage across R1. And if we could find the current coming into here, then we could, and we know one of these currents, we can get the other current too. So there's a lot of cool stuff that we could do. But in this problem, since we only know the resistances of R3, which is 3 ohms, and R2, which is 6 ohms, we could combine these together. Okay, so I'm going to redraw this circuit up here. And I'm going to try to draw it very carefully. And I'm going to combine these two resistors together into one resistor. And that's my horrible drawing of a resistor right there. So this is the equivalent resistance of R2 and R3 in parallel with each other. And what we learned is that R2 times R3, the product over the sum. And this should be a 2. There we go. Well, you may not get a whole number in this part, but after you multiply it by the voltage and current, you'll get a whole number. But in this puzzle, we do get a whole number for the overall resistance here. So R2 times R3, that's 3 ohms times 6 ohms. That's going to be 18 ohms squared. Okay. And then the sum of that, 3 ohms plus 6 ohms, that is going to be 9 ohms. Well, that means that equivalent resistance here is going to be 2 ohms. Okay? So we know now that this is a 2 ohm resistor. The combination of those two resistors is a 2 ohm resistor. And I'm going to draw that ohm symbol a little bit better. And we know this is getting a current of 3 amps. So that means 3 amps is leaving. Okay, and I'm going to draw that here. So that 3 amps is leaving. That 3 amps is coming across, and red is 3 amps going down, going back across, and coming back in. And this is 3 amps at all points. That means the 2 ohm resistor is getting 3 amps. And then 3 amps goes through it and then comes back in. So what that means is that our resistor is getting come on, click, there we go, is getting 3 amps. And now we could calculate the voltage. Voltage is equal to current times resistance, so 3 amps times 2 ohms is going to be 6 volts. So now we know the voltage consumed by this one resistor, and that means we know the voltage created by the battery, which is 3 volts. Whoops, I meant 6 volts. 3 amps times 2 ohms is not equal to 3. It's equal to 6 volts. All right. So that means we know now that this is 6 volts. This battery is getting 6 volts. Okay. I'm going to mark up the current while I'm here. This is 3 amps. This is 3 amps. So all of the red currents are 3 amps. Okay. And there we go. So now we know that these two resistors combined together are 2 ohms, and getting 3 amps, they'll both be getting 6 volts. So that means we know this is 6 volts. If the battery is 6 volts and it's in parallel with R3, that is 6 volts. And R2 is 6 volts, because that is a consequence of Rule 3, which is the loop rule. 6 volts gets created, 6 volts gets consumed. 6 volts gets consumed, being also in loop with 6 volts here. Another way to do it is the outside loop is creating 6 volts, and R2 is consuming 6 volts. So we could do that. Pretty cool. Well, now we have 2 of the variables for Ohm's law. 6 volts divided by 3 ohms is going to be 2 amps. So now we know what blue is. Blue is going to be 2 amps. And that means 2 amps is leaving here. So 3 amps is coming in, 2 amps is leaving. Well, now we know what green is. Green has to be 1 amp. And this has to be 1 amp. Another way to say that is by looking at the actual problem here. Whoops. I'm going to keep drawing those 1 amps. This is 1 amp. And 2 amps coming in, 1 amp, 3 amps, so everything's adding up perfectly. What we could have done also, instead of doing it that way to get the 1 amp, is say 6 volts divided by 6 ohms is 1 amp too, as well. So once we get one of those components, the puzzle just falls into place. And there we go. That is how to combine 2 resistors in parallel to get 1 resistor. All right. Let's practice. Let's move on with a little bit more of a difficult problem. I want you to go ahead and try to find the resistance, currents, and voltage of each component below of this puzzle. And now we have 3 resistors that are in parallel. Okay. So go ahead and try this problem. The battery is producing 200 volts. This resistor is 100 ohms. This resistor is 100 ohms. This resistor is 100 ohms. And you could probably get this problem without having to combine the resistors at all. You could probably just do it really quickly, doing it the old way too. Well, not the old way, what you've learned. So there's a lot of ways to do this one easy problem. So go ahead and pause the video and complete the circuit. And we're back. Let's go ahead and try this one. So we know this is 200 volts, and using the consequence of we don't know the current, we know the battery is producing 200 volts, and using Kirchhoff's loop rule, we know that this has to be 200 volts because it's in parallel with this, and using a mid loop here, whoops, we know that the current coming to here is also getting its own current, which is going to be supplying 200 volts. And we know this last resistor is getting 200 volts. So we could just actually go ahead and put 200, 200, and 200 right here. Okay. And what we could find out here, if this is 200 volts, 100 ohms, this is going to be 2 amps through this section. So I'll go ahead and draw that. And I'm going to use green to draw that. Actually, I'm going to use green to draw R3 this time. So we know R3 is getting 2 amps. Okay. Well, we have another resistor that is in parallel with R3 and the battery, and that is also getting 200 volts because that is a consequence of rule 3. So 200 volts divided by 50 ohms. So 200 divided by 50. So what is that? 4. Let me just check. I have problems adding it. 200 divided by 50. 4. Awesome. So that is going to be 4 amps. Okay. So we know that this resistor right here, and I'm going to call it blue, is getting 4 amps. Okay. And finally, this last resistor, R4, which is in parallel with the battery. So the battery's producing 200 volts. This has got to be consuming 200 volts. 200 volts divided by 100 ohms is going to be 2 amps. Even though it is the same current as the current going through R3, it is a different and its own distinct current. So I'm going to label this guy pink. I like pink. It's a cute color. All right. Well, what that means is that using the junction rule, I'm going to use red to define the junction coming, the current coming from the battery. I'm going to use red, and that means the current coming from the battery is coming back into the battery. That is red. So the current coming from the battery into this junction is red. Green is leaving. And an interesting way of looking at it is if green is leaving, we still have blue and pink leaving on the other side. So in a way, we have 2 separate currents that are actually, if they combine, they'll combine to a unique color, but you could look at them as 2 separate currents overlapping on each other, right? And then when blue separates out into the next junction, you still have pink left over, okay? And for some reason, that pink current disappeared. So I'm going to call this pink. So let's go ahead and track this. You have red coming in, 2 amps is leaving through one path, and you have 4 amps plus 2 amps leaving on the other path, right? So if 2 amps, so red is coming in and 2 amps is leaving, plus another 2 amps, another 4 amps is leaving on another path. Well, that means 4 plus 2 plus 2, 4, 5, 6, 7, 8. That means red, and I'm going to copy this over to make it easier, is going to be 8 amps, and that's red. That means red coming in has to be 8 amps, right? Okay. And that means 2 amps on the bottom is leaving. It has gone through this 4 ohm guy, and it's going to be combining with that 4 amps. And those currents will be combining together. And they're going to then be combining with the 2 amps. That's going through R3 and getting the 8 amps again. That's going back into the battery. And so what does that mean? That means this is 8 amps. Okay? So that's how I track the current in going through this. There's another way to do this problem, which is more difficult. You combine the 2 resistors together, R2 and R3, and I'll go ahead and do that right now. And I'll make a little bit of room. Actually, I'm going to undo that. All right. So that's going to be 8 amps there. I'm going to actually start up a whiteboard, and I'm going to do this problem, and I'm going to combine those resistors onto another problem. So what I'm going to do is go to this, and I'm going to take a screenshot, and I'm going to do this another way, the same problem, even though we know the answer. See if I can get the whole problem this time. And I'm going to go ahead and copy that in as a prompt. And we're going to draw this right here. So we know this battery is producing 200 volts. Oops. So we know the battery is producing 200 volts, so I'm going to go ahead and draw a little battery right over here, producing 200 volts. That's my battery. I'm going to label it, and we know R3, it looks like that is going to be, oops, edit, undo. And I think it's trying to correct me. I'm going to make that little guy a little bit better looking. Make R3 a little bit more squiggly. And I'm going to erase this and make that look like a better looking battery. think if somebody has a history of being able to draw pretty well, they'd be able to draw these little things better. All right. Well, we know this battery is 200 volts. So we're doing the same problem again, but we're going to do it a different way. And we know this resistor, which is R3, is 100 ohms. Okay. We're going to draw another resistor here. Okay, and that is going to be R2, which is 50 ohms. And so this is R2, this is R3. And then finally, so we're just copying the same problem. All right, fine. I'll use your weirdness. This is going to be R4, which is 100 ohms. What I'm going to do is I'm going to apply that one consequence, well, that one part of Rule 3 for the Kirchhoff's loop rule, that we could combine two resistors together to be one resistor. So let's do that. I'm going to redraw this. And I'm going to combine R3 and R2, and I'm going to call that okay, so this is the 200 volt battery. So R2 and R3 combined. So basically this is the, actually I'm going to refer to that as R23. When I combine two resistors together into one resistor, you're supposed to designate it like that, as R23. This is going to be the, since they're in parallel, it's going to be the product over sum. It's going to be R2 times R3 over R2 plus R3. And that is what R23 is equal to. So this is going to be 100 times 50. Okay, so wow, that's going to be a big number. What is that, 5,000? 5,000 ohms squared divided by 100 plus 50. So that's going to be 150. And so in some of these, when you combine them together, you actually will get a fraction sometimes. So that's 5,000 divided by 150. So that's 33.33. So 33.33 ohms. Okay. This is what we get for that. And now we have R4 way out here. And R4 is still 100 ohms. Okay. So now what I'm going to do is I'm going to scooch down a little bit, and now I'm going to combine R2, R23, and R4 into one resistor. Okay. So I'm going to zoom back in. Oops. I'm going to draw the same battery. It's 200 volts. But now I'm going to call this R234. And now I'm going to combine these two resistors together. Well, R234 is going to be equal to R23 times R4 over R23 plus R4. Okay, so this is going to be 33.33 ohms plus times 100 ohms over 33.33 ohms plus 100 ohms. So what we're going to find out in a second, I'm going to use a calculator, is that this probably will work out to be a whole number. So that's 33.33 times 100, 3033, so no shocker there, 3033 ohms squared divided by 133.33 ohms. So now we know R234 is going to be the product of those two divided by the sum. So I'm going to divide this by 133.3333. And you get 25. All right. So this is going to work out to be 25 ohms. All right. 25 ohms. 25 ohms. Okay. So now we know this is 200 volts. This is 25 ohms, right? So that means it has to be consuming, edit, undo. It has to be consuming 200 volts. And 25 ohms divided by 200 volts divided by 25 ohms is 8 amps. So we could have combined, and the reason why we did that is to find out exactly how much is coming out from the battery. And we found out earlier that that was 8 amps, but we did it through a different way. Okay, so you could combine this, oops, edit, undo. You could combine these guys together in this way and just by little chunks, do two at a time. And I drew it out over a long period of time, so I'm sorry for the length of that, but I wanted to show how I'm thinking about things. And so you could immediately get the 8 amps. So let's move on to another problem. We have a battery that is 9 volts. It's producing 9 volts. We have R2 and R3. R2 is 3 ohms and R3 is 6 ohms. We don't know the current and voltage. R4 is 9 ohms. We don't know the current voltage. So this is a puzzle that you could solve multiple ways. Try to find the current resistance and voltage of all the components. And let's see how you do. Good luck. Go ahead and pause the video and do the easiest method possible. Whatever inspiration and calculations you can get in the easiest way. Pause the video now, please, and try it out. Right, we're back. Let's go ahead and do this, and we're going to do this a little bit quicker. We have a battery producing 9 volts. That means this is 9 volts. In the loop rule, third rule shows that this is 9 volts, and that means that R4 is 9 volts. 9 volts. Okay. Well, if R4 is 9 volts, 9 volts divided by 9 ohms is going to be 1 amp. Okay. So we know that the arrow coming out, another arrow, so the arrow, the current leaving the battery is the current coming into the battery. so the current is leaving the battery, gets to this junction right here, and it's going to now split. It's going to split. Oops, edit, undo. So we're going to draw a different current, and we're going to call R4 as blue. And then it goes back in and combines back up with whatever goes through R2 and R3. R2 and R3 are on their own branch, so they are going to be a different, oops, well, I'll just use that guy to go through here. So R2 and R3 are their own voltage, green. Okay, so I've tracked the current. And so red is coming out. It goes into this first junction. Green leaves, blue goes through R4, and we know R4 is 1 amp. So I'm going to go ahead and draw 1 amp. This is going to be R4 is 1 amp. And this is 1 amp, and this is 1 amp. All right. Well, we don't know what the red current is, and I think how we're going to find the red current is by finding what the green current is, because we know the blue current, we know the green current, and the blue current plus the green current is going to equal to the red current, right? So in order to do that, we have to combine these two resistors together. Well, R2 and R3 are in series with each other, so that behaves just like a 6 ohm, just like a 9 ohm resistor. So what I'm going to do is just draw a little itty bitty drawing right here, and this is going to be R2 and R3. Okay, this is going to be 9 volts. R23 is going to be, well, it's going to be R3 plus R2, which is going to be 9 volts. Oh, well, that means this guy is not 9 volts. I'm sorry, that is 9 ohms. Well, R23 is in parallel with the battery, which is 9 volts. That means this is getting 9 volts, and that means that the green current, thank you, the green current is actually going to also be 1 amp as well. Okay, so even though it's the same current, it's a same number as the blue current, it is a separate current. So that means the green current going through R23 is 1 amp. Okay, so we know this is 1 amp. Okay, and that means 1 amp is leaving, another 1 amp is leaving, the 1 amp is joining up with the other 1 amp, the blue amp, 1 amp coming in. So that means this is getting 1 amp, R2 is getting 1 amp, and R3 is getting 1 amp. Okay, and now we could calculate the voltages. 1 amp times 3 ohms is going to be 3 volts. 6 ohms times 1 amp is going to be 6 volts. Okay. And now we have a means using the junction rule. We have red coming in, blue leaving and green leaving. Blue is 1 and green is 1. So that means red has to be 2. Red is going to be 2 amps. And that means this is 2 amps, 2 amps, and 2 amps. So that means That means this is 2 amps. Pretty cool. Another way we could have done this is combined the resistors, R2, 3 with R4. Okay. And so we know R2, 3 is going to be 9 ohms. And we know R4 is 9 ohms. Well, to combine all those together, you have to go R23 times R4 over R223 plus R4. And I'm going to erase this squiggle right here. That's just supposed to be a multiplication symbol. R23 times R4. So R234 is going to be equal 9 times 9, which is 81, ohms squared, over 9 plus 9, which is 18 ohms. Well, 81 divided by 18 is going to be equal to 4.5. Again, when you combine these together, sometimes you get a fraction. Can't do much about that. And so now we have one circuit. We have just one circuit. Let me redraw that. So I'm going to redraw this circuit right here. So this will be 9 volts. This is going to be 4.5 ohms. And that means it's consuming 9 volts. And 9 volts, okay, so 9 volts divided by 4.5 is 2. So what we find out that this has got to have 2 amps flowing through it. So again, if you combine resistors together, you could get the total current coming out from the battery. So I'm actually going to make that red. So that means this is going to be 2 amps. And that means the battery is producing 2 amps. So you could combine resistors together easily to get the 2 amps. And you just do it in little chunks. I chunked these two together to get 9 ohms. And then I put these two, R2, 3, in parallel with R4 to get 4.5 ohms. And then you know the voltage then, and then you could get the current. So there's a lot of ways you could have done this problem. I kind of like the first way, a little bit easier. All right. Next problem, we have a battery that has it's in parallel with a full branch, with a branch that has its own sub-parallel branch. This is a really good problem because it forces you to combine all 3 rules together. So you have 20 volts. The battery's producing 20 volts. You have R1 that is a 2 ohm resistor. We don't know the current and voltage. We have R2 that is 4 ohms. That is in parallel with only R3 that is 12 ohms. R2 and R3 are in parallel with each other, but this whole branch, this small sub-parallel branch, is in series with R1. And this entire branch is in parallel with the battery. Some people would, I've heard some students in the past say that, oh, R2 and R3 are in parallel with each other, and then they're in parallel with the battery, so this is 20 volts, this is 20 volts, and this is 20 volts. That is not true. R2, 3 are only in parallel with each other. This entire branch, R1, R2, and R3, are in parallel with the battery. So you're going to have to combine all these resistances together using what you've just learned, and then get the voltage there. So please go ahead and pause the video and try the problem. Okay, we're back. Let's go ahead and do it. We know this is 20 volts. That means this entire thing is consuming 20 volts. We have this right here, which is R1 is 2 ohms. So I'm going to start off by redrawing this. Oops. I'm going to undo that. I want to go ahead and make this as easy as I possibly can. I'm going to draw the battery. And I'm going to draw the resistor R1. That's R1. And R2 and R3, I'm going to combine those together to one resistor. And I'm going to call that R23. Now I'm going to copy the values for this over, for R1 over. R1 is going to be 2 ohms. Make that a little bit of a better drawing. R23, when I copy R23 over, I've got to do it as product over sum, just like we learned before. So 4 ohms and 12 ohms, that's going to be 4 times 12, so that's going to be 48 ohms squared. And resistor over the sum of that, which is 4 ohms plus 12 ohms, which is going to be 16 ohms. Okay. Well, now we've got 48 divided by 16. They're in parallel, so that's why we get product over sum. 48 divided by 16 is going to be 3. Oops. Let's draw that again. 3 ohms. All right. Excuse me. And so this is going to be 12 volts. 20 volts is the battery. All right. Well, we could further reduce this down into one system, into one resistor. We could reduce that 2 ohm R1, R2, and R3 into one resistor, which we're going to call R23, R123. Okay, so this is R123. Okay, so that is going to be, so R1 is now in series with R23. Even though R23 is a sub-parallel branch, and they're in parallel with each other, and that's why we did this, R1 is in series with this, as you can see right here. So R1 plus R23 is going to be equal to, and I think R1 is 2 ohms, and R23 is 3 ohms. So that means R123 is going to be 5 ohms. And that 5 ohm resistor is in parallel with a 20 volt battery. Okay? Well, that means that this guy, this 5 ohm resistor is consuming all of that 20 volts, right? And what does that mean? Well, that means that 20 volts divided by 5 ohms, that has got to be getting 4 amps. Okay? So that's Ohm's law. So what that means is that 5 amps is leaving the battery. All 5 amps is traveling across this top wire. all 5 amps is going, 4 amps. I apologize. Why am I writing 5 amps there? Go back to that. This should be 4 amps. 4 amps. And all 4 amps is going through that resistor. 4 amps is going across there, and 4 amps is going in. Well, now we know how much current is leaving our battery. Okay, so let's backtrack this current. This current, the same current that was here, is going to be in this circuit that we drew as well. It's going to be in this circuit that we drew. So that 4 amps is the same 4 amps here. It's the same 4 amps there. It's the same 4 amps going across this. That means this is 4 amps. And this is 4 amps. 4 amps. And then 4 amps, right? And then backtracking further to our beginning, that means 4 amps was leaving our battery in the beginning, traveling across. All 4 amps is traveling down through R1. It's then being split up into this junction into 2 different currents, and I'll just use blue and green again. Oops. Gonna undo that. So now I'm going to use a different color for, so I'll say blue is going to the right, going down through that to R3, R2. It then is going to combine, and then we're going to get a different current that is going through 2, 3, is going through 2, that is combining. And then finally, come on. Yeah. Those 2 guys are combining back to the 4 amps. So 4 amps comes into this subparallel branch, and then 4 amps is leaving. Right? So now we know, using this method, how much current is leaving the battery. Well, that's going to help us, right? Because that means 4 amps is being produced by the battery. So we know this 20 volts is this 20 volts is this 20 volts. So that's no different. So that's 4 amps. And since R1, 2, 3 combined is getting 4 amps, we can see here by tracking this version of our circuit that R1 is getting 4 amps. And that same 4 amps is being brought up through through R2 and R3. But 4 amps going into R23, which is a 3 ohm resistor, now we could calculate voltage, right? So R1, we could calculate, right now, we could calculate the voltage that this guy's consuming. So if R1 is getting 4 amps, that is going to be 4 times 2, which is going to be 8 volts, right? And so 4 amps times 2 ohms, 8 volts. So we know this guy is consuming 8 volts. And we can mark that here. But the cool thing is that R23 is also getting 4 amps. So we could use this to get the voltage across here. So R23 is getting 4 amps. So 4 amps times 3 ohms. That's going to be 12 volts. So 12 volts. So that means this guy is going to be getting 12 volts. Well, that tells me that this is 12 volts. 12 volts. And then R2 is 12 volts as well. Because if R23 is 12 volts, then that doesn't mean this gets 6 volts and this gets 6 volts. Remember what we learned before, that since it's in a loop, you know the voltage here, and it's in parallel with this voltage, they have to be the same voltage, and those two combined are just 12 volts. Okay? We've learned that before in a couple, in the earlier couple videos, actually. So now we could calculate the current through here. 12 volts, 4 ohms. 12 volts divided by 4 ohms is 3 amps. 12 volts divided by 12 volts is going to be, 12 volts divided by 12 ohms is going to be 1 amp. Okay? So this is how to combine all, a bunch of resistors together and then solve a puzzle. Okay? So you're going to use this to finish the tutorial on Kirchhoff and Ohm's Law 2. So please move on to that and do that lecture tutorial, fill it out, and send it back to me through Canvas. Thank you very much.